one of the ways that we can think about calculus is as a deep dive to the study of functions. So we need to begin by basically reviewing a lot of things that we know about functions. So take a moment to review in your head and see if you can think of a good description of what is a function. Pause the video if you need to think about what is a function. Now, when you think about what a function is, a lot of times students will think of one of these two different types of definitions. And so here is this. This is a mathematical definition. A function f is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. And then we can go on to say D is called the domain of f, and E is called the actually codomain of f, and it contains the range of f. Now, all of this is a very technical definition, and alongside any technical definition, it is really important to have a practical working definition that is sort of like how you think of this thing. And so I really encourage you to think of just a function as some sort of a process which takes an input and returns an output. So it takes input values and it converts them into certain output values. So for example, the squaring function, it takes an input of 3 and it returns an output of 9. Okay, so it's important to really have this kind of practical working definition of a function as just a thing that converts inputs to outputs. And yes, it is important to have this technical definition under your belt as well, but that is something that you pull out for specific cases where you're like, I don't know, is this a function or is it not? A lot of the times you're going to be able to we're going to be working with functions where they will be understood to be functions, and so we won't have to work so much with the technical definition. Okay, so representing a function. Here is a function, or rather there is a function in this story, and let's see if you can figure out what the function is. So I went on a bicycle ride, and at each moment in my ride, I was at a particular elevation. What do you think is the function that is being represented here? What would be the inputs and what would be the outputs? At each moment in my ride, I was at a particular elevation. So in this case, we have the times of my ride, the moments of my ride would be the inputs, and then the output would be the elevation. At each moment, that would be the given information or the input. I was at a particular elevation, that would be the reported information or the output. So here we say my elevation was a function of time. And so the time would be the input and the elevation would be the output. And this is a verbal representation of this function. Okay? Now, I can take this same function, and of course, I can get a phone app that records my elevation at several different moments during my ride. So I can get a table of values from my phone app. And this gives me a numerical representation of this function. Back here, I just had a verbal description. Okay, this is describing what the function is doing. Here I have a numerical description of the function. And then of course I can take these numbers and I can turn them into a visual description of my function, aka a graph, right? And that graph is really a whole picture of what we saw in the numerical representation, right? So these all go together, but then the graph gives you other information. For example, you can see that like my elevation went up and then it stayed the same, roughly the same for some amount of time, and then it went down. And you can talk about how rapidly my elevation went up and how rapidly my elevation went down and for how long I was at my maximum elevation. So each of these descriptions and representations of this same function, all of these were really the same function. All of these representations give you some different information, and they are all useful and they go together. Okay, so these are 3 of the 4 typical representations of functions. The fourth, these are 3 of 4. So can you think of what the 4th representation is? 4th representation, so we talked about verbally, my elevation is a function of time. At each moment in time, I had a particular elevation. Numerically, this was the table of values. Visually, that was the graph of the table of values. Algebraically would be if I had some sort of a formula. Now, most real-life functions of things that we actually do in the world, like ride a bicycle, don't have an algebraic formula that represents them. We can approximate them by modeling with an algebraic formula, but those aren't exactly the values, okay? Now, in math classes, we typically only work with the algebraic representations, or not only. We often do work with all of these things, but we generally only work with functions that can be represented algebraically as well as in other ways. So let's look at an example of that. So here is another real-world data, or a real-world example that involves some data. So here's the world population P as a function of time. And so T is the number of years since 1900. So T equals 0 means we're at the year 1900. Population here is represented in millions. So this basically says the point where T equals 0 has P equals 1,650. Take a minute to think about what that means in terms of what year and what was the population in that year. Pause the video if you need to. So what does this point here, this point 0, 1,650 represent? So 0 years since 1900, that means in the year 1900, the population was 1,650 million people, which was 1,650,000,000 people. Okay, so this would be a verbal description of the population, that the population is a function of time, and then specifically saying if we measure T to be the number of years since 1900. Here that we have a table of values, which gives us a numerical representation of this function. And here we have a visual representation of this function by plotting those individual points, numerical values. And we can turn this into an approximation, a modeling of the function. And we're going to use just an approximating function, which is given here. And I used another program to basically calculate what is the best fit function for this data. I'm not worried about that. What I'm looking at is like here now is an algebraic representation of not exactly the function of the population, but something that we can use as a function of the population in order to make predictions, for example. Okay. Now, some other vocabulary that we have has to do with the domain of function, domain and range. I want to... So the domain is the set of all input values to a function. Now, in terms of how functions are actually defined, generally functions are defined with their domain. So part of the definition of a function is what is the domain of the function. And if it is not specifically defined, then in terms of if the inputs are real numbers, then we will take the domain to be all real numbers that can be put in this function. So we'll talk in the next section about specific types of functions in our catalog of functions and what sorts of restrictions they have. But hopefully you'll remember some things like I cannot put any negative numbers under a square root. So in this case, we would have to have 3 minus x has to be a positive number, which means that x can't be bigger than 3. So that means x has to be less than or equal to 3. And if I graph this function, then we can see that domain reflected here, that the x coordinates, all of the input values have to be less than or equal to 3. Okay, so we see this function exists basically to the left of 3 and including 3. The range of the function is the set of all output values. Those are represented as the y values in this graph. And we can see that the y values go from y equals 0 on up, and they can get as big as they need to get. So in this particular case, our domain, let's see, can I... Yeah. Our domain would be negative everything to the left of 3. So x is... That is not what I wanted. Less than or equal to 3. And the range is y is greater than or equal to 0. And we typically actually put these into interval notation. And I need to think for a minute about how to put an infinity. Option 5. Okay, so this is negative infinity to 3. And y is greater than or equal to 0. So the range, it goes from 0 to infinity. Okay. That's a better way to write this. Okay. So that's showing that one. Looking at this piece, the thing that triggers us with this function, g, is that we have division, and we can't divide by 0. That's outside of the domain of the division function. So, or the division operation. So doing a little bit of algebraic work, we see that x can't be 0 and x can't be plus or minus 2. So I am going to just let's see, I'm going to get rid of this and I'll graph this function. And something that you might see here, this is a limitation of this particular technology. Okay, that's a little better. So we see that the x coordinates are avoiding 0 and -2 and +2. So in this case, we have domain x can equal 0 and ±2. So if I was to put this in interval notation, that means the things that x can be is everything from -infinity to -2, union. Let me see if I can find a union symbol. There's this union. Everything between -2 and 0. Union, everything between 0 and 2. And then union, everything above 2. So from 2 to infinity. Okay, so that would be the domain of G. And then the range, I am just going to look at the graph for this. Looking at the graph, it looks like the y coordinates seem to be, this graph seems to cover all of the y coordinates except for y equals 0. And sure enough, the output values, there's no way to get a 0 division unless I have a 0 in the numerator, but I have a 1 on the numerator. So, and I'm just kind of going to take the graph as my clue that I can get every other y coordinate. So this looks like y is not equal to 0. So that would be everything from -infinity to 0, union 0 to infinity. Okay. Okay. Now, when we're talking about functions, looking at the definition of function, one of the parts of the definition is that each element x in the domain is assigned exactly one element in the range. Okay. And this is the thing of where no input can have more than one output. Okay. And so, I don't know how. So there is something that we can use as a vertical in order to determine if a function or if a graph represents a function or not. And that is the vertical line test. And let me do this, take a vertical line and run it through. And so what we see is, like, I'm gonna use this left graph here. And the idea of the vertical line is the vertical line represents one input value. So right now in the particular graph on the left, it looks like I'm using the vertical line to represent the x value of, like, I don't know, 1/2-ish. And so I'm looking up and down the x value of 1/2 and seeing how many y values I get from there. And it looks like I'm only getting one y value. And if I take another x value, say x equals -1 in this graph, then I look up and down that line and I see only one y value output. And in this particular graph, I can sort of sweep this vertical line across, and for each x value, I only get one y value. Okay, so it looks like the left graph does represent the graph of a function of x. For this, and we could also talk about the domain and range for each of these. I want you to think about those too. So in this particular picture, it looks like if I sweep across different x values, that's what I'm doing with my vertical line. Each vertical line represents one particular x value. And given any one x value, I'm only seeing one y value in the graph. That means that the inputs, each input is only corresponds to one output, which is great. That does look like this graph represents a function of x, y as a function of x. Now, the third graph, and it's a little bit hard to see, you've got some faded lines, but what we have in the pink is something, let me see if I can kind of outline this. This goes across horizontally, and then it takes a vertical step up, and then across horizontally, and then a vertical step up, and then across horizontally, and a vertical step up. Okay? Like that. And now, as I take my vertical line representing individual x values, I can see that at each integer, for example, at x equals -1, I have a whole interval of y values here. Okay? This graph shows corresponding to x equals -1, I have y equals -2, -1.9, -1.873, -1.447. Okay, I have a whole bunch of y values that correspond to the x value of -1. So this tells us that this graph does not represent y as a function of x, so nope. All right. And the last graph, can you tell, does this represent y as a function of x? Hopefully you said no. We really only need to find one x value that has more than one y value corresponding to it. And so, for example, you can take x equals -1 again, you can take x equals 0, you could take x equals -0.3. Okay, all of these x values have 3 y values corresponding to them. So here is one y value, 2 y values, 3 y values corresponding to that particular x value. And so this shows that this graph does not represent y as a function of x. So this would be a big nope. All right. So the first two did depict functions. We should actually talk about what are the domain and range. The domain is the set of all inputs to the function. Okay. And the range is the set of all outputs. So the inputs in a graph are represented as the x coordinates, and the outputs are represented as the y coordinates. All right. So let's look at the second one first, actually. So the second one, the set of all x coordinates we're using here, I can see x coordinates ranging from there over to here. So it looks like the x coordinates go from -2 to 2, and we see solid dots here and here on the ends of the graph. So that looks an awful lot like closed interval. So the domain looks like everything from -2 to 2, inclusive. And what about the range? The range is the set of all output values, or in the graph, it's the set of all y coordinates that are used. Think for a minute about what y coordinates you see being used here. What we have is, it looks like all y values from, looks like y equals -1 here, and the highest y value looks like y equals 2. So my y coordinates seem to go from -1 to 2. Okay. Now looking at this first graph, can you calculate the domain and range? I am actually going to leave that as an exercise for you to think about, partly because it is in fact an exercise that I want you to think about. All right. So this might also come in handy in thinking about some of the next slide, which is the piecewise functions. So take a moment to see if you can remember what are piecewise defined functions. All right, so here are a few piecewise defined functions. Here's one. Here's another one. So depending on how you thought about it at first, piecewise defined functions are really they're defined in different ways on different parts of the domain. So, you know, there's nothing saying that this is a different, like, I don't know, a different breed of function necessarily, but it's in terms of usually the algebraic definition. So on this first function, what we have is a linear definition of the function for x, for the input values less than or equal to -1, and then we have some quadratic function defining it for values of the input that are greater than -1. And the second one, we have one type of linear function on the domain, the part of the domain between 0 and 1, another type of linear function on the part of the domain from 1 to 2, and then a constant function, which is another type of linear function on the domain of where the input is greater than 2. This is another function that can be defined piecewise, and it can also be defined not piecewise. This is the absolute value function. The absolute value function, y equals the absolute value of x, you don't really have to define it piecewise if you say it's the absolute value of x. You could also say it is the distance from it's the distance from x to 0, or the distance of the number to 0. And that is not a piecewise definition in that verbal description. But, and there's even in the algebraic description, this is like writing y equals absolute value of x, where we have that symbol that means absolute value. That is not a piecewise definition. But one of the ways to write an algebraic definition when you don't already know what the absolute value is, or when you need a working definition, one of the ways to write the absolute value function is as a piecewise function. You might want to remind yourself of what those two different pieces are, and actually take the time to remind yourself what these two linear pieces are and how that definition relates to the verbal description of the absolute value of a number being equal to the distance from the number to 0. Okay, and so here's a question. Can you think of any piecewise defined functions from real life? Good question for you to ponder and think about. Okay, when we're talking about functions, there are some descriptions that we have of functions, and one of the descriptions we will use in talking about functions is symmetry. Okay, so here is a function that has some symmetry to it. Symmetry, basically, the word actually breaks down to sim. Do you know what sim means? Take a minute. Sim is a, I believe, Greek root that means same, as in it's very it's part of the word similar. It's the part of the word see, I'm thinking of only other words that are basically symmetric. But similar is also another word that comes from the same root. I'm not thinking of others right now. And metric, this is a measurement. So symmetry is a quality of having a same measurement somewhere. So there's a few different types of symmetry that we have encountered. And if you look at this graph and you think about what kind of symmetry you see here, you might be able to think about this being a symmetry that you could fold this graph in half across some center line, namely y equals 0. And one of the things that we have in terms of number line and numbers is we have a symmetry across the number line, right? The x equals 0 is a reflective point between a number and its opposite. Okay, so here is some point A and its opposite. And if I look at, here's where f of A is, okay? For this value of A, f of A is this number, whatever it is, negative 5 point something. And if I look at what f of the opposite of A is, it is actually the same. So basically, in this graph, where I see this symmetry where I could fold it in half, where like the left side is reflected in the right side and vice versa. Another way to say that is if I take symmetric inputs, then the outputs are the same. So if I compare the outputs for symmetric inputs for A and negative A, that the outputs are the same for those two symmetric inputs. When we have a graph that gives the exact same outputs for symmetric inputs, do you remember what we call that graph? Or what we call that function? It is called even. Okay, and somewhere, okay, make that black. Okay, so this is an example of an even function that we have here. So this function is, f is even. Okay, let's hide these bits and let's look at another function. Now what is happening with this function? This is g. And I want to look at symmetric inputs. I'm going to look at, again, symmetric inputs. Here's an A and the opposite of A. Okay. And you might notice that there is some symmetry here, and it is different from the symmetry of F. Okay, so if I look at, here's G of A, where is G of the opposite of A? I'm going to go ahead and show it here. How are the outputs related for these symmetric inputs? You might notice that the outputs are symmetric as well. The outputs are opposite. Okay? So we can write the same thing when a function gives opposite outputs. Do you remember what you call this function? Well, if we're going to call one function even, we can call the other function odd. Okay. So here we have opposite inputs and opposite outputs. Now, let's see if I can think of, okay. So not every function is either even or odd. For example, I mean, I could just change this function a little bit. I don't know what this is going to do. It's going to do something. Okay. So I have changed this function somehow, and now if I look at opposite inputs, so my inputs are still symmetric, but I'm looking at my outputs. Here, my G of A is like -1, and my G of -A is like 2.5-ish. And if I look at how the outputs are related for opposite inputs, it doesn't appear as though the outputs are related to each other in any predictable way for the symmetric inputs. Okay, so this particular function would be neither even nor odd. And you don't call it anything, you just say it's neither even nor odd, okay? It's kind of like if we have the words even and odd for integers, 2 is an even integer and -7 is an odd integer. The number pi is not an integer, and we don't have a definition of whether pi would be considered an even or an odd number, okay? All right. Last example here of showing other symmetry is this example. And this example is, there's a symmetry here which is different from the even and odd symmetry. Now, we can actually talk about symmetric inputs here, and this particular function does actually have even odd symmetry. Can you figure out which one. But the other symmetry that I wanted to show here is actually a different symmetry where the function seems to repeat itself, which is a different type of symmetry. It's just like it's showing we have the same thing repeated. And the fact that it is repeating itself shows, I don't know what this, oh. I don't know what. I'm supposed to be able to draw something, I think. Okay. My sketch is a little bit screwy. My apologies. But this is called a periodic function, and the periodic functions that we tend to get are trig functions. They're also sometimes referred to as circular functions or cyclic functions, where we have this repeating symmetry that this particular graph, I just want to hide these pieces because they don't make any sense. This particular graph shows a period of 6, okay? That if I pick any input value, let's say at x equals -2, and then -2 plus 6 is 4, that if I look at the output value, it looks like the output value is somewhere around there, and here looks like the same output value. Okay, so like this point on the graph corresponds to the same with an input of 6 more. Okay, anytime I have two input values that are 6 apart, the output values will be the same. Okay, so that is a periodic type of symmetry. And our primary examples of periodic functions are all of our trig functions. Okay, finally, we need to talk about what increasing and decreasing means. There are some very technical definitions of what increasing means and what decreasing means. I want you to look at those, and I want you to take those technical definitions and spend like a solid minute like thinking really hard about how those technical definitions basically mean if a function is increasing, that means as you follow the graph from left to right, as you read the graph from left to right, the y values are going up. And decreasing means as you read the graph from left to right, the y values are going down, okay? Or the output values are going down. So this is as the function is increasing if the graph goes up, and the function is decreasing if the graph goes down. So on this particular graph, it looks like the function looks like it's increasing from for all x values that are less than, say, -3. It looks like the graph is decreasing from input values of -3 to +5. And it looks like the function is increasing for all input values greater than 5.